Hello, everyone. Welcome to yet another Harmony Data Science Summer 2022 cohort live coding session. Happy to have you here with me. As always, my name is Julo Christian. I'm the Assistant Program Coordinator at Harmony. We've had a series of live coding sessions, our 8th in the series. And today we'll be talking on doing a live coding session on time series data, that's time series data analysis and modeling. So definitely this will be related more to the data science track, but of course there's analysis in there too, and there's modeling, so everybody's welcome to learn also. So today, taking us on today's session, we have Arinze Ezirim, is a junior data engineer at Harmony AI Labs. So he took us on the previous session, that was on Monday. So today we'll be handling this session also. So without wasting time, thank everyone for joining, those on YouTube and on Zoom here. I'll just invite Arinze to kick off. Arinze, you have the floor.
Hello, good afternoon, interns. Welcome to today's section. We'll be discussing today time series data analysis. And our workflow for today, we'll see how do we wrangle a data set that is actually a time series data. And then we'll take what factors can we infer to make a data set to be time series. And then we'll progress to the basic procedure we use when wrangling a data analysis project, possibly checking maybe the data types, making sure that it has the right format, taking for null values and the rest of them. And then that will lead us to progress into key concepts in time series analysis. Concepts like seasonality, stationality also. We'll see how we can test to see if our data sets which are working with is seasonal, or if our data set is stationary or non-stationary. And we have some basic procedure we use to determine that. We use the DFK test, and also we run some plots, the autocorrelation function, ACF and PACF. From that, we'll progress to the models available in time series analysis, the likes of the AR, autoregression, the MA, moving averages, the ARMA, a combination of the AR and the MA, which is AMA. We'll progress also to using the RMS to see how it works, where you have to go through integration between the AR and the MA. And then also SARIMA, that gives you seasonal RMS. And from after looking at these models, getting a theoretical explanation on how they work, then we'll progress to model a time series data. And afterwards, we'll see how we can run some forecasts using some models. So that will be our workflow for today. So let's get the ball rolling. I will share my screen now, and we begin in essence, in NS. Okay. Sorry. I hope my screen is audible enough. Hope it is clear. It's visible, right? Hello? Is my screen visible? Okay, there's no feedback. Okay. Now for this live coding section,
yeah, can see.
Okay. Yeah, for this. For this section,
yeah, started sharing.
Okay, for this section, we'll be working with the data set index 2018. Okay, let's import that immediately.
Yeah.
Okay, good. Let me check for that data set again.
Yes, we can see this now.
Okay, no problem. Thank you for the feedback. Okay, let's import the data set. Okay, I've run the first cell already. Getting the libraries I'll be requiring for the work. Yeah, that is it. Okay, df equal to pd.reach underscore index 2018.csv. Okay, yeah, before going to the coding, let's have a basic of what a time series data is. Okay, now, a time series data, this is a sequence of data points that occur in successive order over some period of time. Now, what that means is if our data set is ordered such that our observations follow a sequence with respect to time, now that makes that data set to be time series. And there are some other features we check. Now, in that data set now, can we find trend? Is there a trend in our data set? Is there a season? Now, these are things, these are pointers we infer to see if our data set is actually a time series data set. Basically, we check the trend and the seasonality. The trend can actually be, let's say, maybe an upward, maybe let's say an upward trend or a downward trend. Or can have seasonality in the case where, as let's say, for a period, we observe, let's say, some movements, and after a while, we observe same movement in the future. Now, the basic of a time series analysis is we are trying to study the present and the past so as to forecast the future. And in that future we're forecasting, there's a likelihood that previous patterns will still come up in the future. So in such a case now, such data sets can be seen to be a time series data set because one will have trend, we have seasonality, we have pattern. And from the pattern, that pattern should persist to the future. That is what we've seen in the past can also or should also be present in the future. And that is why we try to build models that will study the present and the past so as to give us or to predict for us what the future should be. And this time series analysis is very much used in the financial markets where we trade the likes of stocks and forests, because definitely we get numerous data from such finance bodies, And those data we get, they are time based. They are time based. Like what I have here on my screen now is actually a data set from the stock market where we have SPS, that is S&P, DAX, FSTM, and Nikkei. So today we're trying to understand this work and run some basic analysis and modeling with the data set. Okay, let's run some ED on it. Already we've seen our head. Okay, let's check our shape. df.shape. Okay, 6,269 observations with about 5 features. Let's check for missing values. Okay, we have no missing values here. Okay, let's check out description to see the brief statistical description of what we're working with. Describe. Okay, let's check out data type. Let's check DF info. Let's see if we can get our data type here. Okay, what can we observe now? We have about 5 features: date, SPS, DAX, FTSE, then Nikkei. But then if you observe now, our date data type is reading objects. Now that means, what do we do in such a scenario? Now for a time series data, our date feature has to be a time date. So the first thing we have to do now is to convert the date feature from object data type to a date time data type. And we use the pandas to date time to do that, to achieve that. Okay. Sorry. df dot pd. Time dot date, then default equals true. Okay, now if you observe what I use here as the parameter, the date first here. Okay, let me do dot head. Let's see how this will display now. Dot. Okay, yeah, that date first is telling me that I should have a sequence whereby I have the year, the month, and the day. That should be the order I wanted. I use that to be true. Also, for a time series data, our index also has to be a date. So what that will mean, let me put comment in distance, please, in case we request for this. Okay, so we'll convert also our date feature to be our index. So we'll set our index now. That gives us df dot set index date place equals true. Okay, let's confirm that then. df dot head. We can see now, so we've taken off our earlier arrangement we had here of 0, 1 to 4 to now have our dates as our index. Let me comment this. Date feature. To index. Okay. Also, we can try to run, we can also set our frequency, because in a time series data, the observations can be, let's say, it can be daily, it can be monthly, it can be yearly. Now, from what we have in our head, if you observe now, I have here 1994, 01, 10, 1994, 01, 11, 1994, 01, 12. That means that this observation we are taking on a daily basis. So we can set our frequency to be daily, because now in a time series data analysis, the period has to be the same. The period has to be the same. And Pandas provides us, let's say, an avenue to set our frequency. The frequency can be daily, monthly, weekly, or yearly as per annual. So let's set our frequency now. To do that, we'll have df equals df dot as freq. Now, because our data set here is daily, we'll have it to be B. Okay, let's use D. Then I'll show you something now when I do that. D. Sorry. Let me show you something now. Dot head. Now, if you observe now, using D daily has given us some null values, any values, which is 0, 08, and then 09. Because normally in the stock market, stocks are not traded during weekends. So, but this D stands for every day, that is from Monday to Sunday, including the weekends, Saturdays and Sundays. But since our stock are only traded on business days, we have to use B. B now stands for business days as against D. Let's do that now. Okay. Let's do this now. Okay, if you observe now, the 8 that came up earlier and the 9 have been removed because we used B to be our frequency of our data sets. Okay, let's check for missing values in this one we've gotten now. Let me comment this, please. Okay, we've gotten some null values now. Possibly it means maybe there are some days in which maybe, despite being a business day, maybe truck weren't traded on that particular day. So that was led to these null values. And in taking care of null values, or in filling of values, we can go through different techniques. We can go to the imputation, which will involve, let's say, maybe doing a back fee or a front fee, or possibly filling with the mean, or going to interpolation. So let us use a simple technique here to fill our data set. Let's use maybe a forward fill for this now. Fill method. Okay, let's do the same for dash, then we'll check once and for all. I hope you are following what I'm doing.
Yes, wow.
Okay. Okay. Let me feed you that using backward feeding. What's the other name? HDSC. df.ftse dot fill any method and the last df dot nickel. So let's confirm again if the data set has been filled entirely or missing values. Okay, we've achieved that then. So, okay, let's have a plot of what we have here also. Okay. Okay, so now we've done at least some data wrangling. We've tried to convert our date to the date time. We'll set our date also as index. We'll set our frequency for business days, and also we filled missing values by imputation. Now, in time series analysis, now data sets can either be stationary or non-stationary. Now, what do we mean by saying that this data set is stationary or non-stationary? Now, by stationary, we mean that the data sample has, if it's stationary, has a zero mean, that is one, or a constant a constant mean or zero mean, a constant variance, and then no autocorrelation. These three features. Now, if a data set has these three features, that means that that data set actually is stationary. One, having a constant mean or a zero mean. Two, having a constant variance and has no autocorrelation. Now, this no autocorrelation means it has no relationship with itself or with the past observations. That's for the autocorrelation. And when we try to model a data set in the time series, we try to build or we try to, let's say, generate a white noise. A white noise is a stationary data set that has zero mean, also that has a constant variance and no autocorrelation. Because definitely from what we have here, this is actually from the stock market. This data set is actually non-stationary. But as we progress, you get to know why I made this as assertion here. But let's generate a white noise that is actually stationary. Okay, let's do that now. So let me target Wn for white noise to be equal to np.random. I want to generate, let's say, an observation here that will have the same mean as my, okay, let me do something first. Since I have 4 observations here, which is SPS, DAS, FS, HDSC, and Nikkei, I'll try to analyze just one of the observations, which is SPS. So I will drop DAX, FTSE, and this other one, Nikkei. So to drop that, I'll just use del dot DAX, DF dot FTSE DF dot NIKKEI. I'm coming. Oh. Why am I getting this error then? Why am I getting that error? What is it now? NIKKEI. Oh, sorry, comma. Okay, good. So let's check out df.head. So I have now just SPS and then my date. So I'll try to generate now my white noise, as I said earlier. Now this white noise will actually be a data set that is stationary, and I'll use the mean of this feature, use my SPS observation and standard deviation to also, well, I say, to generate this white noise. So let me do that now. I'll tag white noise to be WN to be equal to np.random normal df.dax then my scale will be .std standard deviation, then I'll make my size to be equal to the length of my data sets. Okay, let's do this. Okay, that has gone. So let me add this up to my data sets. WN to be equal to WN. So df.head okay, I've done that. Okay, so let me have a plot of this so you see what I meant by being stationary. df.wn.plot. So now let's compare the plot for the white noise now, what I have here, and the plot for SPS. I told you earlier that the SPS data set here we have is actually non-stationary, but we'll try to compare these two things. So this has a mean of 0, an equal mean or a constant mean. This has also a constant variance, and also this also has no autocorrelation between the observation and the lags. Now, when I refer to lags actually means previous observations, past observations. That is what I meant by lags. So now, I said earlier that the stationarity is a situation in which samples of a data have identical covariance, that is, has no correlation with a mean of 0. Now, how do we determine if a data set now is stationary or non-stationary? Now, that is done by using the Dickey-Fowler test. Now, in the Dickey-Fowler test, we have two hypotheses. We have the null hypothesis, and we have the alternate hypothesis, that is the H0 and the H1. Now, the H0, which is the null hypothesis, this assumes that a data set is non-stationary. That is the assumption, that a data set is non-stationary. Why the alternate hypothesis, which is that the H1, assumes that a data set is stationary. So now what do? There's a criteria we check to say, okay, now based on this value, this data set is stationary, or based on this value, this data set is non-stationary. Now we check this using the p-value. Now in the Dickey-Fowler's test, it gives us, let's say, an array of numbers: the t statistics, the lags, the p-value, the critical region. So now, when the p-value is less than 0.05, when the p-value is less than 0.05, that means that that data set is actually stationary. Hope you're with me. And then when the p-value is greater than 0.05, that means that that data set now is non-stationary. So let's check now. Let's test our DFSPS and then our DFWM, the white noise, to see if it's actually stationary or non-stationary. Okay. We have to import some modules now. So let's say import stats model dot graphics dot TSA plot as SGT import stats models dot TSA dot stat tools as TST. Then from stats model dot TSA dot seasonal import seasonal decompose. Okay, let's do this. Okay, where that is going, dot AD Fowler DF dot SPS. Okay, let's run this now. Okay, what can we see now? Now, this very first value that has 1.11 is our test statistics. Now, 0.99 is our p-value. This 10 we have here is the number of lags. The 6266 is number of observation. These are 1% confidence interval. We'll have 3.3 minus 3.4, then 5% and 10%. Now, I said earlier, our focus now will be on the p-value, which is this one here, 0.99. You know, I said that if the p-value is greater than 0.05, if it's greater than 0.05, that means, that my data set is non-stationary. And if it is less than 0.05, that means that the data set, oh, okay. Okay. Okay, after this section, I'll drop the data set on my GitHub, please. Okay, sorry for that. So now, because the p-value we have here now is above 0.05, that means that this our observation is actually non-stationary. No, but I said earlier that for a white noise, that a white noise is actually stationary, which has zero mean or a constant mean, a zero variance or a constant variance, and has no autocorrelation. Now let's check the same p-value for our white noise. Fuller df.wn. What can we observe now? Beautiful. Good. Now, our p-value here is 0. And for sure, 0 is less than 0.05. That means that this data set now, the WN is actually stationary. So by using the Dickey-Fowler's test, we can determine if a feature or an observation is stationary or not stationary. And earlier, I did show a plot. Now, this is a plot for the white noise. You can see now, everything here is just crowded, having a constant mean. A constant mean. While for SPS, this, you can see there's a trend. There's a trend. So the mean here is not constant, neither is the variance constant. So this is one way of testing for stationarity. Okay. So let's go to the next concept now, seasonality. Seasonality. Now, by seasonality, what do we try to check here? We try to see, is there a repeating pattern in our data sets or in our feature by seasonality? So this suggests that certain trends that appear on cyclical basis, and usually to test for seasonality, we use the decompose technique. The decompose technique has basically three things it displays for us. It displays the trend, it displays the season, it displays the residual. Now, the residual is like the error between the predicted and the actual. That is the error value actually. That gives us the residual. And for decompose, we have a very basic one we use. We use the naive decompose technique. And the naive decompose technique has two models. We have the additive model and we have the multiplicative model. Now, by additive model, now the observation is gotten by summing the trend, the seasonality, and the residual. That is how the additive model works for the naive decompose. While the other model, which is now the multiplicative model, what it does is it multiplies now the trend, the seasonality, and also the residual. So let's do that right away. Let's run to see for decompose here. Let's say seasonal. Let me use short for seasonal. SEA. Seasonal decompose using the add model. This equals seasonal decompose. Then the observation I want to check, df.sps. Then the model I'm using, I said that I'll be using the additive model. So I have now additive. Okay, let's have a plot of that. Let's see what it looks like. SEA deck. Oh, sorry. What did I use here? Decompose. Hope I run that. Okay. Dot plot. Let's see. Okay. See what I have now. Earlier I told you that it has three basic features you will see now: the trend, the seasonality, and the residue. Now, what the very first one here is the observation. This is the observation. Now, the observation has actually is like the same with the trend. And this is my area of interest now. Seasonality is just a rectangle. It's just a rectangle. This is for SPS. This means that this data set we are working with now has no seasonal variation. So it just oscillates within a range. That's what it indicates, that the observations in this feature just exhibits, or they move in a range, and which you will see very well in, let's say, in the stock market. Actually, those things just go up and down, just having, like, let's say, top and bottom actually, which you observe. But now I saw the work you guys had to read for your stage E. Let me go to that notebook where I did run that code. Okay, now, hope you can see this now. This was the work you guys had in your course content. So when I ran the notebook for that, that should be lesson 4, where we try to get the seasonality. You observe here now, we can see a constant repeating pattern. You can see that here now. That means that this data set given to you in your material has seasonality. But what I'm working with here now currently has no seasonality. So this is one way we test. We try to see, okay, if this data set is seasoned, or it has that cyclic repeating patterns or not. So based on what I have here, this data set has no seasonality. There are no repeating patterns. Then let's now come to autocorrelation function, the ACF. Now by ACF, the ACF tells us, okay, now, because observations normally have different, I say, time, or they occur on different occasions, or different days. Now, when an observation has a relationship with itself, that means that observation has a correlation. But if that observation has no relationship with itself, or neither with the previous observations, that means it has no autocorrelation. And for us to tell if an observation has correlation or not, we now plot the ACF function. So the ACF function helps us to determine if an observation has autocorrelation or not. And to do that, the pandas also gives us another need to do that. So I have, let me run this now. SGT dot plot ACF. Then I have my observation, which is SP, SPS, then I have lags equal to 40. In this case, I'm trying to refer to check the previous 40 observations that I'm trying to do here. Then I have the 0 equal to false. By false, I'm trying to make sure that I don't correlate the first observation with itself. So means I'm only correlating the first observation with the previous 40 observations by using false there as my parameter there. Let me run this. Beautiful. Okay, let's examine this plot closely. Now, what I have here, I have my lags, and I told you that lags refer to my previous observations. Why? This gives us the correlation, because in correlation, the values has a range, and the range usually is from -1 to 1. It can't go above 1, nor can you go below -1. So you have here we have here -2 down to 1. And this is my first observation after the very first one. That is my first lag, is this one here. Now there's a blue region beneath. Now that blue region is referred to as a region of significance. A region of significance. Now, when an observation, which you can see, these are all observations, yeah, when an observation has a plot that is above the confidence interval or the region of significance, that means that that observation has a high significance, which is not 0. Then if you got that explanation, does it make sense? Having the observation above the blue region, that tells us that that feature differs significantly. But if the observation, okay, let me plot for the white noise. Let's see, there'll be any difference with the white noise on. I have SGT dot plot ACF. But there are more technical terms in this time series. That's why I'm taking this time to talk about it before going to our modeling, but I'll try to be fast because I have less time. SPS. Then I have, okay, I'm using white noise now, not white noise. Then I have lags as usual to be equal to 40. Then I have my 0 term to be equal to false. Let's see. Okay, let's check this closely. If you observe now, our observations, just let's say 1, 2, 3, we are formed outside the region of significance. Just 3. Why? For this, all of them we are formed actually above that region. Now this chart tells us that the observation in my SPS, which is my SPS, actually they have correlation with themselves or with the previous observation. That's what it means from this chart. That means in this chart now, there is autocorrelation occurring in the SPS. Why? For my WN, because most of my observations were formed inside the confidence interval or inside the region of significance. That means that this WN observation, that the observation have no correlation with the previous observations or with itself. So by plotting the ACF, we can tell if a feature has an autocorrelation or has no autocorrelation. They're following me. And also for the autocorrelation, the basic principle it checks is that it tries to have a linear, let's say it carries a linear weight from one observation to another. Let's say now, for example, let's assume that this is our first observation now. This one here, my mouse now. It takes a weight from the next one. It takes another weight from this, and all we go to the very first observation. It's like carrying weights from one observation to another. That is for the autocorrelation. But now, for the partial autocorrelation, we try to limit or cancel out the weights in between the observations. Okay, let's plot for the PCF now, PACF. Please, then I'll just talk about the models immediately. We'll just do some modeling and let me not take beyond the time allotted to me. PLT underscore PACF. Remember this for PACF, we check direct relationship between an observation and the feature we are trying to observe. And there's no issue of passing weight from one to another into the observations in between. We don't check that. We just check direct relationship. So I have df.sps. I have lag to be equal to 40. Then I have 0 to be equal to false. Let's plot this. Let's there be any change. Then we'll compare these plots, and then with what can we observe now? What can we observe now from the SPS? Now that means if we check for direct relationship between an observation and the very first observation, you observe now all the points now, they are under the region of significance. That means now, based on the PACF, that there is no correlation now. Based on this, that there is no correlation. If we're using the partial autocorrelation, which normally tries to cancel out indirect weights during the analysis. So let's check for that of the white noise. Let's see what we'll have from there. Plot PACF df.wn lag equal to 40. Then I have 0 equal to false. Okay, what can we infer from what we have now? If we compare that of the SPS and that of the white noise, now the white noise still has like almost the same plot with what we saw for the ACF for white noise. Just 3 observations occurring outside the region of significance. But for the white noise here, the same thing. Now that means that when we going through the ACF, the PACF function, that the WN, the white noise, and the SPS has no autocorrelation. But using the ACF now, which is the autocorrelation function, the SPS has a correlation with the previous observation, while the white noise has no correlation. And this has tried to map out the features of a stationary data. I said earlier, it must have a constant mean or variance, which we observe using the plot we saw earlier. I said also, it will have no autocorrelation, which we've seen now by plotting the ACF and also the PACF. So with this now, we can now progress to modeling. Now, there are different models we use when working with a time series data. We have the auto regression, which is the AR, the moving average, the MA. We have a combination of the AR and the MA, which is the AMA. We have also the ARIMA. The ARIMA has a combination of the AR and the MA, but with a new term now, which is the I, integration. And this integration is the differentiating. The differentiating actually is the difference between an observation and another. That's for the modeling. So I'll just quickly go to the modeling section and just run for AMA that has AR and MA. Then I'll take questions afterwards. I've taken beyond about the time given to me. Sorry, please. Okay, let me do that right away. So let me build my model. Okay, now the theory behind the AR model actually is, it assumes that in the modeling that an observation will have a relationship with a previous observation. So that means we tend to see how an observation varies with the past observation. We check that relationship. So let's build the model immediately. So to build our model, we have to import. So from start models .tsa ARIMA model import ARMA and also from scipy.stat the distribution import chi-square. Let's run this. Okay, now I've been done. So now, but the AR model works very, very well with stationary data. So let's take that now. It works very well with stationary data, and this data also is independent of time. So let's build our model. Let me say model AR to be equal to AMA. Sorry. I have df.spx and my order. Now for the AR has a parameter of p Yeah, y for the MA is a parameter of Q. Y for RMAS that has a integration, which is the differencing, it has a parameter of D. So here I have an order. Let's build a simple AR model. An order of one, that is one observation, and then zero for that, because this is like saying P comma Q. This P is for AR, YQ here is for moving averages. Okay, let's run this. Okay, let's print our results. Result for AR to be equal to model AR dot fit then let's print our summary statistics results AR dot summary. There's something I've not done. I've not split my data set into train and test. Let me split my data set into train and test, please. So I'm coming size. I'd like to use sorry. I'd like to use 80% for my train and use 20 for my test. So let me declare that now, please. Integer len of df.sps multiply by 80 and I have, let me use df train to be equal to df sps dot ilog. So I will take everything from the zero index to size. Size then is the observation before size, and then my df tests to be equal to df sps dot ilog. I have from size then to everything. Let's run this. Okay, let's be sure we're not overlapping. Let me see, df train dot tail let me be sure it's not overlapping, please. Then let me do df test dot head. Df test dot head. Frequency B head. Comment. Let me check something then. series frequency. I have to see what data set. So df train.tail, df test.edge, to 20%. Is that why it's not coming up? To show that can come in. Let me come in df train, df train. Let me run this first. Let's what I get. I'm coming. df train, df train.tail, df test.head. Sorry, subject has no attribute SPS. SPS. Yeah, this worked out fine. Or do you want me to do this? I'm coming. SPS. df SPX. Should I use the entire data set or what? Let me the entire data set. Let me see why this is not working. df df Okay, then let's do this then. Why is my head not working? Why is this not giving everything here size? Then dfi log size to everything. What am I getting error here? Can't get my head. df train test head is empty. Okay. Wow. Okay, so for our training now, this is where we have to place focus or attention to. These parameters we have here: the coefficient, the standard error, the z-test, the p-value, and then the confidence interval for 5 and for this is 5% and 1% or so. So now because in the AR model, it has 3 basic parameters. We have the constant value, we have the coefficient, which is this, 0.99, and we have the residue, which is E. So, but we'll try to check our p-value. That we'll check here now, because our p-value here is 0. Our p-value for the AR model is 0, and 0 is less than 0.05, that means we have to accept the null hypothesis. We accept the null hypothesis, and that means that there is a significant difference from 0 based on the AR model. That's what it means, that there is a significant difference from 0 based on the AR model. Now, if we try to do this for the MA model, let me just copy this. Copy. Paste. Change this to MA. Still the same SPS. Now this will become 0. This becomes 1. Okay, let's compare the values we have now. We have 0.99, 0.00 here. Yeah, 0.00. What about the coefficient? 1288.69. So you see almost the same value. Oh, sorry, no, I didn't change this. This should be MA result, MA result, MA. Still coming up. Okay, let's compare the values now. So I have now 0.9791, 0.00, 0.00. Why? For the AR model, we have, so the very first constant value has a p-value of 0.2. So it means there's a difference between the first lag, which is this, and the very first observation, which is 0.2. Now, based on this difference, we can say that there is a significant difference between the observation and the first previous observation. That's what it means. That means that the first observation has a weight it plays in forecasting the next or the next feature, or in predicting the future per se, because now there is a difference between the constant the p-value for the constant and the p-value for the very first observation. While for the MA model, we have both the 0.00, 0.00. So based on the MA model, you observe that the MA model doesn't take into cognizance the previous observation. It only checks the error residue, or the residual error. That is the principle guiding the MA model. And that is why we have here 0.0, 0.0, telling us that there is no relationship, that the previous observation has no effect on the future observation. So knowing fully well if our observation, if we are going to work with the MA or the AR or the ARIMA, is all based on the parameters we are looking at or we are trying to use in our model. Are we looking at a feature in which the previous observation has a relationship with what we're trying to forecast, or it has no relationship? So now, based on our SPSS we analyze now, we can observe that previous observations actually has an effect on the present observation and what to come up in the future. And this is what we observe, we see very well in the stock market. that the trend in the previous day can actually determine the trend the next day. So with this now, using the AMA, we've just seen the AR model and the MM model. But we can also try out the RMAs, where we have to bring in 3 parameters in our order: the P parameter, the D parameter, and the Q parameter. So we can always try to let's say, try different lags, because now I use a p-value of 1, telling me that I want us to compare one observation with in my model. I can use a p-value of 2 or 3 or 4. So as we keep trying to tune our parameter, we try to see which model gives us a better relationship to forecast the future of our data set. So with this, I've taken too much time. So I'd like to attend to questions from here. At this point, let's take questions based on what we've discussed so far. And then possibly after that, we can come to the end of the section.
Okay. Thank you very much, Arinze. That was a very interesting session. So we're moving straight to Q&A. I'm guessing the interns, they have questions. If you have a question, you know how we do the drill. Just use the hand emoji, then I'll ask you to unmute, then you ask the question. In the chat, I guess somebody had a question. Someone was asking about white noise. Was that Love It? Were you the one? You can ask your question now.
Hello,
Okay.
can you hear me?
Yeah, we can hear you.
I can hear you.
Okay. I was asking about what's the white noise. I think that this is my first time of hearing that term. What the white noise is. So if you can throw more light on it.
Okay.
Thank you.
You're welcome. Okay, now in time series analysis, I said earlier that our data sets can either be stationary or non-stationary. Now, a very good example of a stationary observation is a white noise. Now, a white noise is a data set that has a constant mean, that is 1, a constant variance, that is 2, that has no autocorrelation. Now, what that means is that that observation has no relationship with itself. Now, a white noise is a clear example of a stationary observation in time series. Because when we ran the Dickey-Fowler's test, we observe that, let me go to that place, we ran that Dickey-Fowler, A-D-Fowler, good. Now, when we ran the Dickey-Fowler test, we observed that the p-value for the white noise, which I actually generated now, when I did using the np dot random.normal, that is here, good. I just tried to, like say, to hypothesize a data set actually that will have a mean as the same as my main data set, which is the SPS, and also have a standard deviation the same as that of my SPS. So I was trying just to like to build a data set that have this mean, and then that will have also this standard deviation. But then, based on the relationship between these observations now, they will have no relationship with themselves, my observations. Now, to prove it right, we now run the Dickey-Fowler's test. When we run the Dickey-Fowler's test for our SPS, we observe that our p-value was 0.995, which you have here. And I said earlier, we have a test, and that test is a range. Okay, if the p-value is greater than 0.05. That tells us that that observation is non-stationary. That means the mean is not constant. The mean is not, the variance is not constant. And then it has relationship between the observations. That's what it means, taking my p-value. But when I run that decay-Fowler's test for my white noise, remember I said the white noise will have is a constant mean, a constant variance, and no autocorrelation. Now, my p-value here was 0. And the rule is p-value less than 0.05. That gives us a stationary data set. And when working for the AR model, the AR model prefers to work with a stationary observation or a stationary feature. Then to buttress that point, we went to plot the ACF and the PSF. The ACF, I told you earlier, this checks the relationship between an observation with the previous observations, which is the lags now. Because my observations now for my SPS, we are formed above the confidence interval or above the region of significance. That tells us that my SPS, that the observations have a relationship between themselves. And that was why all the points we are formed outside the confidence region or the region of significance. But for the white noise, this one I have here, just 3 observations, we are formed above my confidence region or my region of significance. That tells us or tells me that my white noise actually is hitting the 3 features of a stationary data set that has a constant mean, a constant variance, and then that has also no autocorrelation. From the chart we have here, all the points, most of the points are formed within the region of significance, telling us that they have no relationship with the lags. Okay, thank you. Hope that makes sense to you.
Well, yeah, I guess that was a nice
fair enough.
explanation.
Thank you.
Okay,
Thank you.
welcome.
Okay, yeah, Pam, you can ask a question.
Okay, thank you for that. My question is it that we don't usually have stationary models? Because you were talking about the white noise, you have to find a way to relate the white noise with the other data for the time series analysis. So is it that we don't usually have stationary, let's say, data sets that from there you see the trend and know that, okay, this is a stationary data set. And then from there you start thinking about the model to use and whatnot.
Okay. Yeah, we have stationary data sets. Definitely we do. But then you can't just tell, okay, if I say, okay, this data set is stationary or this data set is not stationary. We have a criteria we must check. And that criteria is we check the p-value for the decay-Fowler's test, or we check the ACF function. Just looking at the trends, maybe in the chart, like, I gave the chart earlier, where I gave the chart for the white noise, this, and the chart for SPS, which is this. Just looking at the chart, we can't really say that, okay, this data set is stationary or not stationary. We can't say. So the only 2 criteria we use to determine that is the decay-Fowler's test and the ACF function. I only brought this white noise to show you maybe that we have stationary data sets and non-stationary data sets. That's why I brought the white noise here, just to show that disparity that, okay, we have stationary and non-stationary. Like we observe now that when we ran the decay-Fowler's test for the SPS gave us a very high value above 0.05, which is this 0.99. That means that the SPS is actually a non-stationary data observation or feature. So now, when building a model for this feature now, definitely we can't be looking at using the AR model. because the AI model works better for stationary observation. Are we there now? So now, based on the stationarity, that can help us to determine what model to use. Is it okay, an AR model or an NA model, or the one that has an integration of differencing or seasonality, that is the SARIMA. So this is just to show you, okay, we have seasonality, or we have stationarity and not stationarity, definitely. I hope that is clear enough to you. Hello?
Yeah, I guess so. It hasn't replied, so, but that was a nice explanation. I also understood what you said, actually. Okay, moving on to the next question from Adita Mola. It's asking, saying, when you wanted to decompose the series, I'm reading this question. You use additive for the model parameter in the seasonal decompose method. So his question is, what was the reason for using additive and not multiplicative? And also, how do we know which to use? Yeah.
Okay. Now when you decompose, you are at leverage to pick either of the models, the additive or the multiplicative, actually. Now, if you want your observation such that you want to show that the trend, you want to maybe merge the trend, the seasonality, and the residue in your observation, then you say, okay, let me use the additive model where I have such as, let's say, what is obtainable there. Then if you want the observation now to be, let's say you want to have maybe the trend multiplied by the seasonality multiplied by the residue, then you will not pick the multiplicative. But it's all based on your choice. Okay, I want my model or my observation to be additive, or I want my model to be multiplicative. So you can use any of the models, be it additive or multiplicative. There is no, like I say, there's no strict rule that says, okay, it must be this at this point. It's just based on what you want your observation to be. Then you cannot pick, be it additive or multiplicative. Okay.
Okay, thank you very much for that. Moving on to the next question. I guess this will be the last we have to handle for today. Isaac, you can ask your question.
Okay, good evening. Thank you, Mr. Arinze.
Oh, welcome.
I think I'll start from what you were just trying to explain. You said it's based on what you want to observe or something like that.
Observation.
About additive or multiplicative.
Yeah.
You're talking about the additive or multiplicative method of for the modeling. So I wanted to find out what would initiate your decision to want to check either multiplying the three of them or adding, because I'm not yet clear exactly on how that decision is made.
Okay, let's assume a data set where we have an obvious trend. For example, let's say we have a trend. Okay, for sure, a trend that is one. And then let's say there is no seasonality in that data set.
Okay.
Are you with me now?
Yeah.
Let's assume a data set that has a trend, but with no seasonality. You know, I said earlier, for seasonality, I tend to be repeating patterns per se.
Yes.
In that case now, in such a data set now, such an observation, you know, if you multiply the trend with the seasonality and with the residue, that might actually give you zero. True or false?
Yes, true.
Then you will have zero observation. And in such a case now, you can't actually plot your decompose to see if, to get a chart per se. But if now you have seasonality, let's say it's very, very minimal, you can just use, if I multiply this seasonality now, it will have, let's say, very little effect on my trend, or if I plot this, my seasonality now, it will have, well, let's say not much of a difference per se in that addition. Let's assume now let's say we have a seasonality value. For example, let's say 0.1, and let's say maybe a trend. I'm not giving values now, please don't quote me for my word, just taking values for hypothesis. Let's say our trend now, has a value of 1. Let's say our seasonality S, let's say has a value of 0.1. If you observe now, if I multiply my 1 by 0.1, in this case, for going through multiplicative model, I'm getting a value of, let's say, 0.1, right?
Yeah.
That means I'm giving my observation a weight of 0.1. Now, if I go through the additive model now, I have now 1 plus 0.1. That gives me around 1.1 value now, right? That means that my weight now means I'm giving my observation a much higher weight. So if I want to give my observation a much higher weight for a seasonality that is low, the best pattern to use now will have to be additive now, right?
Yeah.
With me, because I have like 1.1 value, for example. But if I go to multiplicative now, I'll have a value of like around 0.1, giving a lower weight to my observation. So based on having weight for your observation, you can choose to go to the additive or the multiplicative. That is one. And then if there is no seasonality now in your data sets, definitely going through the multiplicative is like giving you 0 observation or 0 weights. In such a case now, the best model to use now will now become additive. Does that help?
Sorry, come again with the last point. I didn't get it clear.
I said now, if there is no seasonality now in our observations, that means now seasonality is 0 now, right?
Yeah.
So if we go to the additive technique, which adds the trend to the seasonality to the residue, in that case now, we'll have, let's say, 1 for our observation weight, right?
Yeah.
But if I use multiplicative now, because I have no seasonality, that will render my weight to be 0. And in such a case now, I will have 0 observation.
Yes.
So based on seasonality, I cannot say, okay, the seasonality now, let me use multiplicative or let me use additive. Does that make sense now?
Yes, I understand.
Okay.
I understand what you
Okay.
said. Thank you very much. Then my second question will be about the last part where we were doing the modeling, where you alternated the orders. The orders when you did for the MA and the other one, AR. I didn't know. I was so clear why you alternated the orders.
Okay, in the AMA, the ARML model, it's actually a combination of 2 models, right? Which is the AR and the MA. Now, the AR has a parameter which is P, trophos.
True.
Yeah, why? The MA has a parameter which is Q, right?
Exactly.
Now, when writing the parameters for the AMA, you write there P, Q. Are you with me? Now, the P stands for the parameter for the AR, and then the Q stands for the parameter for the MA. Now, because I was trying to run using just the AR model, I gave P a value of 1, and I gave Q a value of 0. Now, in that model, I've just run an AR model only without bringing in Q. So it means I have just an AR model in that particular, let's say, line of code. Now, when I now swapped the values, giving P now 0 and giving Q 1, I'm saying that I want my AR-MA model to only work as MA. Does it make sense to you? Now, I want my AR-MA model to only work as MA. And that was why I gave P a value of 0 and I gave Q a value of 1. But you can actually, in ARMA, it's a combination of both models, right? Now, I can also give P a value of 1 and Q a value of 1, combining as in both models. That can also work. So in that case now, I have ARMA working together now. The AR working simultaneously in that model I'm trying to build. But when I use 0, 1 or 1, 0, I'm trying to use just one part of the model in that building, neglecting the other. Yeah, so that is it.
Okay. I think lastly, the in terms of weight, thank you for answering the question. In terms of weight, what are we trying to give more weight to our model, or we're trying to reduce the weight? How do we make that decision on the weight? Because we talked about it initially.
Okay. Now let's, I told you earlier that previous observation, like in the stock market, for example, has a correlation or a relationship with the prediction or the present, right?
Yes.
Now, in such a case now, if I'm trying to consider that previous observation has an effect on my prediction, then I should give a much higher weight to my observation in this case.
Okay.
But when now my previous observation has no effect or has no relationship with my present, then I can take my weight to be at 0 or to be minimum in such a scenario now.
Okay,
good.
All right. Okay, our notebook, we talked about the from our notebook, you said the first plot is usually the observation, and then the next one is the trend. So there's just a very slight difference from our own course material. The difference between the first graph and the second. I think the second graph, which is the trend, shows a smoother trend than the first. I just said, let me just point that out and ask if there's any reason for that. Yeah, this one.
This, right?
Yeah.
Okay. This must have gone through log transformation. That was why it should be like this, basically, possibly. If it had been transformed or so. I didn't take time to analyze what you have here, but I feel this should be due to the transformation that has happened here. That's why you should have this straight line also, basically. Maybe based on the moving averages, rolling mean, and the rest of them. That's why you should have this. Yeah.
Okay. All right. Thank you so much.
Yeah, welcome.
Yeah.
All right. Thank you very much. It was a very interesting session. With that, I guess we've come to the end of today's session. This was very, very interesting. Thank you very much, Arinze. And as usual, this video is always on our YouTube channel. You can always go back and follow along. And definitely we'll send the data sets across to you, like you already said. So go back and watch the video step by step. Any parts you don't understand, you can actually get to understand as you just watch it along and code along. So thank you very much for those joining us, those on YouTube and also on the Zoom. Thank you very much, Arinze. Arinze is a junior data engineer at AI Labs. Thank you very much for this wonderful session. And to the interns, I guess this was an interesting session. You've learned a lot because this is part of your stage E, that's for the data science track, those in data science track. So it was a wonderful time. It was a wonderful live session. As always, my name is Ajulo Christian. Thank you all for having us and see you next time. And as usual, if we have a session, we always make the announcements on the Slack channel. So keep an eye out for that. We might be having other live coding sessions. So with that, we've come to the end of today's session. Thank you, everyone. Have a wonderful weekend. Bye for now.